Okay, good day everyone. Good morning, good afternoon, good evening, wherever you're joining from. We are having another insightful masterclass today on the Precision Agriculture Incubation Program. And today we are going to be talking about Geographic Information System. So we have introduction to GIS and its application in agriculture. So I just quickly want to do the drill before we go fully into the presentation. So, Alright, so welcome once again. This is Britionfield Academy. Britionfield Academy is the host of the program, Precision Agriculture Incubation Program. So this is one of our social impact program, majorly. So our vision at Britionfield Academy is to create a world where every young person, regardless of their background, has the opportunity to become a digitally savvy farmer or agricultural professional, driving sustainable and equitable growth in their communities through the transformative power of technology. And our mission is to raise the next gen farmers that are tech inclined and digitally savvy. So Britionfield Academy is a social enterprise where we train and build the capacity of young professionals in modern and emerging technology for the future of work, and most importantly to lead with precision agriculture. So we have core 3 methodology. Number 1 is education and knowledge sharing, training and skill development, coaching and mentorship. And we have 6 tech skill in focus. Part of them is drone technology, GIS and remote sensing. We have data science and agriculture, robotics and Internet of Things, artificial intelligence and machine learning, and lastly is enterprise development. So we're leveraging drone technology to be able to collect data and help youths develop capacity in the concept of precision agriculture, how they can farm better in a data-driven way. Okay, so what's our motivation? Why do we do what we do? Or starting the academy, or even running a program like this, Precision Agriculture Incubation Program? Yes, because from our research, we discovered there's a skill gap that needs to be closed. So this academy and this program was strictly created to be able to help young professionals build the required technical and enterprise skill for the future of work in agriculture. And also, observing the trend is not just enough. Not just being aware that, okay, artificial intelligence, machine learning is now changing the game. We actually have the vision that youths need to become an enabler and player in the fourth industrial agricultural revolution, and not just mere observer by becoming a part. And thirdly, technology is actually the key to unlock the African agriculture potential. So with technology, we can do much more. We can save resources, save cost, and also farm efficiently and profitably. Yes, by leveraging data. Okay, so why should you join us? The reason why you should join us at Britionfield Academy is that we are creating the future we want in agriculture. And we've discovered this, so we are on the right path. We also connect you to the world of information and opportunities, which comes in terms of scholarship, internship and volunteership programs on both local and international scale for your career growth. Also, we are big on skill development through project collaboration, university symposium, workshops, and community interactions. And lastly, we also give you access to coaching and mentorship from industry leaders and professionals around the world through our courses and programs. So at Britionfield Academy, we are building a community of young tech-inclined and digitally savvy farmers and professionals. So we have various courses from drone technology to GIS to data science, robotics and Internet of Things, machine learning, and enterprise development. So for this program, Precision Agriculture Incubation Program, we have various partners here. Integrated Aero Precision, a agricultural drone company in Nigeria. We also have Dev Global. Dev Global is based in the US. It's an international global company too. Our speaker that we have today actually works with Dev Global. So He's going to be sharing more of his background and what he is doing at Dev Global to us and be able to benefit from his wealth of experience. We also have DJ Academy, Dev Afrique, ISPA, that's International Society for Precision Agriculture. We have AAPA, that's African Association for Precision Agriculture. And we also have in Nigeria for our on-site location, three core universities. We also have agricultural courses in their school. That's Federal University of Agriculture, Abeokuta for Ogun State. Then we have River State University in Port Harcourt. And lastly is Federal University of Technology, Mina, Fort Mina in Niger State. So, okay. So without wasting much of our time, I quickly want to bring up the speaker so we can have. So today we are discussing in details an introduction to GIS application in agriculture. Okay. Just give me a few seconds. I quickly want to bring up the speaker's profile. That's what I'm trying to add to. Alright, so I quickly want to read through our speaker profile before I bring him on board. So his name is Simos Girati. He's a dedicated geospatial specialist and program leader working in the intersection of health sciences, technology, and humanitarian action. As the NASA Lifeline program lead, he empowers decision makers with health observation data to enhance disaster response and resilient efforts globally. With a strong foundation in geography and geospatial information system (GIS), CMOS brings a system thinking approach to complex challenges in global development and emergency management. He also serves as a GIS and geospatial specialist at Dev Global, a mission-driven partnership that supports international organizations in leveraging data, innovation, and technology to drive social impact. CMOS collaborates with multidisciplinary team to deliver actionable geospatial insights, supporting projects across sectors including public health, climate resilience, and humanitarian relief. CMOS earned his bachelor's degree in geography from the University of Denver, where he focused on geospatial technology and applied mapping for development and environmental change. His work brings the technical and human dimensions of global challenges, advocating for the ethical use of geospatial data to support vulnerable communities. His core strengths lies in GIS and remote sensing, Earth observations for humanitarian application, programs and stakeholders management, disaster risk reduction and resilience. Lastly, data for development, D4D, and interagency coordination and knowledge translation. So it's my pleasure to bring to the podium our speaker for today, Mr. Simos, will be joining us live now. Hello, can you hear me, Mr. Simos?
Yes, I can hear you well. Can you hear me?
Yes, I can hear you very well. Okay, you have the floor now. Let me just bring up your slide.
Awesome. Thank you, Joseph.
All right, you're welcome. Okay.
Perfect. Yeah,
Okay.
great. So you can go ahead and go to the next slide and we'll kick things off today. Thank you for the warm introduction, Joseph. As Joseph mentioned, my name is Seamus and I am a consultant with Dev Global. I've worked with them and very closely with Dev Afrique, our kind of partner organization that's based in Lagos, over the last 4 years on projects across the kind of geospatial gamut. So including conservation, looking at global health, humanitarian response, disaster response, and others as well. And happy, as there's time at the end, to field any questions, and I'll share my contact information for folks as they're curious or would like to connect on any of the specifics. But having a kind of experience applying geospatial technology, remote sensing, to some of these global challenges that we face in international development and global health. And so today, with some of the background, my educational background is in GIS and geography, as well as remote sensing, and also global health. So those are the two things that I studied and have been applying that to my work. And today, I'm going to kind of break it down a little bit, and we're going to walk through a couple of different things, looking at GIS principles, kind of a basic introduction to concepts and different things in geographic information systems. And then I'll speak a little bit to remote sensing, and then we'll get into some applied examples in agriculture. And throughout the presentation, I'll tie things together, tie things into agriculture, as I know that is the main focus of the cohort that you all are in and how you're applying yourselves. So let's go to the next slide. And you can go ahead and click one more forward for me. So starting with some fundamentals, let's chat through a little bit just to set the stage here. So GIS stands for Geographic Information Systems. At its core, GIS is a comprehensive framework designed for gathering, managing, and then analyzing spatial data. Spatial data is unique because it combines location information, so the where, with descriptive information, the what. So you can kind of think of it as another layer deeper than kind of data science or working with spreadsheets and data, which many of you might be familiar with, right? This data has some sort of component to it that describes where it's taking place on the planet. And so this allows us to then understand phenomena, what's happening, what we're trying to measure in a geographical context. This is important because it significantly enhances our understanding of the world and the intricate systems we are all a part of. So by enabling us to visualize these complex relationships and patterns, GIS empowers us to make more informed decisions and effectively solve real-world problems across various sectors, including agriculture. Next slide. So here, just to kind of showcase some of these different sectors, you can see agriculture on the slide there in the bottom left, and that's what we're going to be honing in on today. And I'll get into more detail about the specifics, but you can also see global development up there being kind of a far-reaching, and many of you might be familiar with the Sustainable Development Goals through the United Nations. So geospatial data and the things that I'm going to kind of be talking through today work in service of measuring, monitoring, evaluating, and proving progress essentially towards these global development goals, looking at infrastructure planning, urban development, land use change monitoring, and so forth. A lot of these kind of can fall underneath the global development umbrella, global health being one of those. And that's where a lot of my experience has been over the last couple of years, working on different disease eradication campaigns, but you can do mapping, health facility access, vaccination and health campaign facilitation, and microplanning is a big one. And then route optimization. So how can we get vaccines from point A to point B, or where are folks that are experiencing a disease outbreak, and how can we get them the things that they need as fast as possible. A couple others on the slide: policy, humanitarian response, conservation, just to give you guys a sense. And I'll save some time here and won't read through all of those, but we'll share the slide deck as well, so folks have access to this as a resource moving forward. But just to kind of set the stage a little bit and kind of help folks understand just the breadth of application of this technology, right? Geospatial and geographic information systems are tools and data that can be applied across all of these different contexts. The next slide, so I'll kind of dig in a little bit more into agriculture, and then we'll kind of revisit this towards the end of the presentation as well. But as you can see, agriculture, we have crop monitoring. So this looks like real-time monitoring of crop growth and conditions using satellite imagery and remote sensing, which I'll share more about. These these tools using GIS and remote sensing can help us identify areas of poor health or stress early, supporting targeted interventions. Kind of going catty corner across the slide, we have crop health and productivity, which is very similar, but you can use multispectral satellite imagery and different kind of calculations and methodologies to understand crop vigor, nutrient deficiencies, and pest infestations, and enable precision agriculture at scale. I'll talk a little bit more about the NDVI, which stands for Normalized Difference Vegetation Index, but basically using satellite or drone data, you can tell the health of down to, depending especially if you're using drone imagery, down to like the specific plant. And then of course, compare that across the field and identify zones where a pest might be infesting the crops or where part of the plot isn't receiving enough water, stuff like that. Other ones on the slide, climate modeling and forecasting. So you can predict climate patterns at local and regional scales, right? There's an abundance of climate data out there that has been being collected by satellites and different remote sensors, and as well as like in situ data that can be kind of paired together to help you understand the climate and understand what the future might look like. So to inform planting, scheduling, irrigation, and more. And then land suitability analysis is the last one I'll touch on this slide, but you can combine a bunch of different data types, and I'll call them layers, which I'll explain more, like soil type, slope, rainfall, and land use. GIS can help assess where specific crops are most likely to thrive. This reduces trial and error and improves long-term agriculture productivity, and as well saves the farmers and people that are trying to plant crops money and time over the long term. So on this slide, I'm going to kind of start to get into some of the nitty gritty around GIS. So these are two screenshots of a Google map. And if any of you are familiar and have used Google Maps on your phone or some sort of other mobile navigation application, maybe Apple Maps or Waze or different things, you have different base maps that you can use. On the left, so this is an example of maybe like the normal base map that you would see on your map as you're kind of navigating around town. And on the right, this is a satellite image. But as you can tell, they're representing the exact same scene. You can see kind of in the middle, there's a soccer or a football pitch with a track around it. And you can see how that shows up in the satellite image. And then you can see where that shows up in the other map. You can see roads, you can see rivers, and how the features are represented. I like to show this image first before I start getting into talking about the different types of geospatial data, because there's two common ways that geospatial data is categorized: vector data and raster data. Vector data is like what you see on the left, and these are points, lines, and polygons. So you can see, for example, there's a point on the football pitch that says University of Lagos. So this is an example of a discrete point somewhere on Earth, represented by an X and Y latitude, longitude coordinate on the map. And so you can see that showing up on the left as a point. You can see the University Road is the road just to the north, and you can see that represented on the map as a line. And then you can see the green kind of oval around the University of Lagos sports complex point, and that is a polygon, right? Because that's a two-dimensional shape that's more than a line and a point. So we're working with those three. If you remember anything from today, remember points, lines, and polygons represent vector data, and that's what you're seeing on the left. And then on the right is a satellite image, but this type of data is called raster data. Which essentially you can't see it in this image, but if you were to zoom in super far, this image would be made up of pixels, right? Like looking at your computer screen or a TV, our eyes don't pick them up because they're so small. But if you really zoom in, our screens are made up of probably millions, if not hundreds of thousands, if not millions of pixels that are each portraying a specific color. And then as we zoom out, it starts to make sense as an image to our eyes. And so this is the same way that satellites and drones see the Earth's surface as they're scanning and collecting information by pixel to then piece together an image. So raster data are pixels. You can kind of think about them like that and think of them as like satellite images or drone images. There's other types of raster data as well, but we're going to kind of stick with this simple understanding for today to kind of build a foundation. If you'll go to the next slide, I'll talk a little bit more about vector data as I just explained. So it represents features on the Earth's surface as points, lines, and polygons. Points, as I mentioned, are single points on the map, or single locations. Lines represent linear features, so think about roads, rivers, bike paths. And then polygons represent areas on a map. So for example, buildings, or one that is commonly used in global health, for example, and I can give an example here in a second in agriculture, but in global health, polygons oftentimes are administrative boundaries. So thinking about state boundaries, province level county boundaries, different things like that, settlement, village boundaries, stuff like that. In agriculture, it might be property lines and plots and different borders. You can think of those as polygons. Vector data is usually linked to attribute tables containing descriptive information about the features. And we'll get into attributes a little bit later, so not to confuse you up front. But information can essentially be attached to those points, lines, and polygons. And like for example, what we just saw, where the point was attributed with the name of the University of Lagos, for example, or the University Way was an attribute to the line feature that represented that road. So that's a little bit of an introduction to vector data. The next slide, we're going to talk a little bit about raster data. So again, raster data, if you'll go to the next slide for me, thank you, represents features on the Earth's surface as grid cells or pixels. So each grid cell has its own value. You can kind of see in the graphic on the right of how those pixels actually look as you start to get closer. And so this is ideal for continuous data, which just means data that is less discrete. Like a point is a very discrete thing on a map. Elevation, for example, temperature, land surface are things that are kind of described as continuous data. So they will go for miles and miles and miles, or essentially cover the entire surface of the Earth, right? Temperature can be measured at any point around the Earth. Land surface type, elevation, those sorts of things are continuous. Raster data is derived from remote sensors. So as I already kind of talked a little bit about, that means sensors or satellites, airplanes, drones, which have a lot of applications specifically in agriculture. Satellite images are common types of raster data. So you'll see some examples here. I have most of my experience working specifically with satellite imagery, and I can speak a lot more to that than drones. I can probably learn a thing or two from you all about drone applications, or would be curious to hear if we have time for discussion at the end, what you guys have seen. And then the resolution size of the grid cell impacts the level of detail in the data, right? So like what size is the pixel that the satellite, drone, airplane is collecting on the surface of the Earth then determines the resolution of the image. And so higher resolution images mean smaller grid cells, pixel sizes, and you can identify smaller features in these images, right? High resolution is typically considered less than 5 meters per pixel. So you're starting to be able to detect individual buildings, different things like that. Like the Google satellite image we just looked at is a very high resolution satellite image. There's other types of satellite images where the resolution, you wouldn't be able to pick out different buildings out of the imagery. You might be able to see what neighborhoods look like, but the detail isn't as fine in those images. One last slide. This next one is just kind of a comparison between vector and raster data. I'll wait for the slide. There you go. Where you can just see how these two can be used interchangeably. So like vector data and raster data, there's oftentimes specific use cases that it makes sense for the data to be in that specific type, but there are ways to transform it back and forth depending on the type of analysis that you're running. It also depends on the type of instrument that you're using to collect the data. For example, if you're out in the field with a GPS tracker and you're dropping coordinate points along a line, then that is an example of collecting vector data. But if you're flying a drone collecting images, that is an example of collecting raster data. But you can kind of see how vector data can be presented as in raster format and vice versa. And geographic information systems have basically processes and built into them the softwares that would allow you to transform things back and forth. The next slide, coordinate reference systems. So this is a bit of a trickier concept, maybe not theoretically, but then when it comes to application, I remember getting kind of tripped up with this one when I was first learning. But essentially, the world is a three-dimensional, right? So the world is a giant sphere. Most of the maps that we are interacting with on our phones, on our computers, or even paper maps, right? They're flat. They're two-dimensional, and they're oftentimes distorted because you're taking something that is spherical and you're projecting it into a rectangle, which doesn't necessarily add up mathematically when you think about the surface, land surface, and shape of different things as they appear on a globe versus onto a flat map. So to accurately locate and display our spatial data that is collected out in the field as a satellite is passing around the Earth and collecting information, or as I'm walking down the street in the field collecting latitude, longitude points, we need coordinate reference systems, or for shorthand CRS, to be able to then understand and interpret that data in a geographic information system and to make a proper map. So both vector and raster data must be attributed with location data. We've kind of already talked about that. This oftentimes looks like X and Y coordinates, or latitude and longitude. And so what a coordinate reference system does, it defines how this data is projected onto the Earth's surface, accounting for the spherical shape on a flat map. And so while working, there's ways that you can work with data, and essentially it kind of standardizes the data that is collected from all these different sources, so you can kind of put it into a coordinate reference system and it's going to make sense spatially, right? Because that's the whole point of all of this, is understanding where things are happening in space and time. And we need it to be accurately represented because we're going to do calculations on the distance of point A to point B, or we need to know what types of crops or the health of crops in this specific part of this field. And we need to know that down to the meter, right? Or centimeter resolution. So it's very important to have accuracy when it comes to the coordinate reference systems. And kind of under the hood, there's a lot of math that's going on. What's nice is today we have computers that do that math for us. So I'm not going to get into the weeds here, but just something to understand and be thinking about. Because as you start to work in GIS, what you'll notice is you'll load a layer one of these days, and it happens to everyone, and your points, you have a data set that's made up of a bunch of points, and you're trying to load them into Nigeria, and you load them onto the map, but then for some reason they're way off in the middle of the Atlantic Ocean. And obviously you know that something is wrong, right? Those data points represent points in Nigeria, not in the middle of the Atlantic Ocean. And so what is happening there is likely the data is being represented in a different coordinate reference system than the one that your project, the map that you're trying to create, is set to in the Geographic Information System. This next slide, maps, layers, and attributes, is kind of an important one, and I've already spoken to a couple of these things, but maps are made up of multiple layers, so often including both vector and raster data. Again, this is why it's important that they're all kind of standardized beforehand, but you can see on the right there, think of these layers like transparent sheets that are stacked on top of each other to make a map. So you have parcels, you have zoning, both examples of vector data, and then you have topography, which might be represented by a raster layer, and then you have wetlands, demographics, land cover, imagery, base map sort of thing. So a map that you might be producing doesn't need to have all of these things. But the cool thing about GIS is that you can layer all of these things on top of each other, and then you can really start to see patterns. You can do all sorts of calculations between the different layers. So as you kind of see on the left, roads, rivers, population density, satellite imagery, these are all example layers in a map. And each layer, as I just mentioned in the last slide, will have an associated attribute table. So attributes describe the features in the layer, and these can be searched, filtered, and used to perform analysis. Okay, so think of it like an Excel spreadsheet or a CSV if you've worked with those, right? So every entry in a vector data set will have attributes associated with it. It might just be a number indicating that this is like 0.1, 0.2, 0.3, 0.4. But you can see in the screenshot example that these are geographic points. So each row is its own point, and then each row is attributed with the information that is in each of the columns. So parcel ID that starts with 8618, the ID for that one is 0, and it's zoned as residential. And the address of that is 7728 Streamside Drive, and then it gives the zip code, state, and tax region as just example fields, and we call these attributes that are associated with the data to help us understand and do more kind of complex analyses. So again, think of it, as very similar to data science, or working with spreadsheet data. So GIS software, I'm going to talk kind of briefly about this. There's a couple of different ones that are out there. ArcGIS is a very popular one. It's the one that I learned on in school, and many of you might have become exposed to it, whether you know it or not. A lot of times when you're looking at dashboards online or story maps, for example, or maps that are kind of like professionally made, these are oftentimes made with ArcGIS Pro. It's produced by Esri, which is a very large company, and they provide software and solutions to folks around the world. It's widely used in government and enterprise. QGIS is one that I like to highlight because it's open source, which means it's free and available to anyone with a computer, and there's versions of it that go back years and years, so you don't necessarily need to have state-of-the-art technology to be able to run it. It has very similar capabilities as ArcGIS. The main differences between QGIS and ArcGIS is QGIS is more kind of it's less polished, I would say, right? So like I would even argue maybe more tools and different analyses that you can run that are pre-scripted for you in QGIS, because there's such a large community of folks out there that have developed solutions, and there's a good way for people to be able to share those in the QGIS community. But it's a lot less polished. The interface isn't as clean as ArcGIS. And I will say ArcGIS, especially in today's day and age, as so much is moving towards the cloud and online compute, ArcGIS has an online version that allows you to work in an online environment and access different things like cloud resources for computing, which becomes important when you're working with large data sets that your computers might not have enough RAM or processing power or graphical processing to be able to keep up with the analysis that you're trying to run. A couple of other ones on this slide: Envy, Google Earth Engine, Python. I will say all of these are good. Envy is oftentimes used with satellite imagery and remote sensing. Google Earth Engine is kind of a one that's also used a lot of times with large data sets that you can go into Google Earth Engine and query them and be able to pull down small subsets of them without needing to download the data set that might be hundreds of gigabytes. You can pull down a specific using an area of interest over potentially a crop field. You can pull down a specific area to get climate data that goes back 50 years without needing to pull down the whole data set that might be the size of the whole country or even continent sometimes. And those become very large and, of course, very heavy, large file sizes, that sort of thing. A lot of the kind of coding language of choice for GIS is Python. ArcGIS, QGIS, both are kind of built on Python and have a lot of Python plugins, and you can a lot of interfaces in there where you can actually build models and use Python if you're savvy with it. Also, Google Earth Engine, different things. There's tons and tons of resources out there. I learned Python specifically for GIS, and nowadays with artificial intelligence and chatbots and just resources online, it's not easy, but there's a lot of resources at your fingertips to be able to try and learn about Python and how to code. Not something that's necessary for getting into GIS though. Let's see. I think we're good to go to the next slide. Yeah, and so now that's kind of a bit of the foundation that I'm going to lay for GIS basics. And we'll share these slides because it's going to take some kind of refreshing over time to really kind of latch on and get, understand some of these different concepts. And really what it took for me was getting my hands on some of the data. And so if you're really curious and interested in learning about learning GIS and having that as a tool that's in your toolkit, download QGIS and start to play around on it. I can share some links to some tutorials that are free and provide the data and walk you through step by step. And so you can start to kind of apply, because that's how I learn in a hands-on way. And the beauty of this technology, again, is that there's so much resource out there for you to be able to learn and do it yourself. So now I'm going to build on all that, as I said, and talk about some remote sensing concepts. Remote sensing is a field in its own, but closely married to GIS, because oftentimes remote sensing is kind of a method of collecting satellite imagery, as I mentioned, or remote sensing is a method of collecting raster data, and that looks like satellite imagery, drone imagery, or aerial imagery by an airplane. But then once you get that data, you then need to analyze it, understand it, put it on a map, do different things with it, and that's when then you would put it into a GIS to work on it. So remote sensing, depending on who you talk, is either closely intertwined with GIS, it might be housed underneath GIS, but they build on each other for the most part. So just a kind of definition here for you guys. And we could spend a long time here, right? There are entire degrees that are focused on remote sensing. So this is really the tip of the iceberg and skimming across the surface for you all. But as I mentioned, it's the process of collecting information about the Earth's surface without making physical contact. So it uses remote sensors mounted on platforms like satellites, aircrafts, or drones. And then these sensors detect reflected or emitted radiation, such as visible light, infrared, or microwaves. And then this information that is then captured by the sensors on these crafts can be analyzed, and we can monitor various aspects of the Earth's surface, including land use, vegetation health, water bodies, and changes over time and space. Common vehicle types. I'm going to talk a little bit about vehicles and sensors. So common vehicles for remote sensing sensors are satellites. We can think of this as these are the ones that are the farthest away. And there's a very large kind of upfront cost to getting them up into orbit of the Earth. But then once they're up there, right, there's satellites that have been circling the Earth for decades and collecting consistent information. And this becomes super valuable for understanding change over time and understanding the climate. And they also provide broad coverage. So there's a satellite that passes over every one of our houses probably every day. Oftentimes one satellite, it takes it maybe a week or two to get basically collect information over the entire surface of the Earth. So they often have swaths, which is like the path on the ground that the satellite is actually collecting information, that are kilometers long or kilometers wide. So there's just a ton of data that these satellites can collect in remote sensing. Drones, on the other side, are kind of this very specialized for high resolution local data, right? So you can send up a drone with a sensor on it and you can collect information. You could fly it over your field, and in the span of a couple of minutes, an hour, you would have information about your crop field at an extremely high resolution, right? Where you could pinpoint a specific plant within, hundreds of thousands that are in a field potentially. And this is really valuable for that high resolution imagery, to where you need that really fine data and analysis. I think there's also some cost implications, of course, with drones, but generally less expensive than satellites. And data, like accessing data from satellites, especially at a very high resolution, becomes pretty expensive. So the use case for agriculture, which I know you all are familiar with, that's why drones are such a nice solution to that challenge, because they're by no means cheap, but they are cheaper when you consider launching a satellite into space and purchasing imagery from some of these commercial providers. There are satellite companies or organizations, oftentimes governments, that put satellites up, and then that data is free and openly available, and then you can access it on things like Google Earth Engine and do long-term climate analyses. So oftentimes you're working with both. The third vehicle that I'll speak to is planes, which then kind of collect at the intermediate level. Satellites are in space, drones could be within meters of the ground, and then planes maybe cruising at some point in between, collecting information over a little bit more broad area, but not quite as broad as a satellite, not quite as fine as a drone. So that's the difference there. And then there's often different types of sensors that are on planes or drones or satellites. Panchromatic sensors capture a single band of light, typically black and white images, and oftentimes offer high spatial resolution. Multispectral sensors capture data in several discrete spectral bands, allowing for more detailed analysis of land features. Hyperspectral sensors collect data across a very large number of narrow, contiguous spectral bands, providing incredibly detailed spectral signatures. So those are kind of the three types, and I'll explain all those in more detail in a second here and make more sense of those. And then there's two other types that I'll talk to today. Synthetic aperture radar, which stands SAR, and that uses microwave pulses to create images capable of penetrating clouds and operating day or night. And then light detection and ranging, which uses laser pulses to measure distances and create detailed 3D models of the Earth's surface. The slides are skipping ahead. If you can go back potentially to the slide that has the electromagnetic spectrum. I think we may be having some issues with the slide presentation. Bear with us. Yeah, keep going back, a couple more. Perfect, right there. If you go one forward. Perfect. So this is an image of the electromagnetic spectrum. I just said a lot of big words on the last slide that surely wouldn't have made any sense to me if I hadn't have studied it in school. So I'm going to kind of hone in on this a little bit more. So the electromagnetic spectrum is very broad, and you can kind of see this like spanning a very long, like all these different wavelengths. And this gets, I'm going to try to explain this at kind of a high level, but essentially we're getting into kind of light and energy physics here. But understanding remote sensing requires a basic grasp of this electromagnetic spectrum. So remote sensors operate by detecting and measuring different wavelengths of electromagnetic radiation. So radio waves from one end all the way to gamma rays. Each part of the spectrum provides unique information about the Earth's surface, allowing us to see beyond what is visible to the human eye. Different sensors are designed to capture specific parts of this spectrum to gather particular types of data. So you can see in the middle, visible light, that is, you can kind of see the rainbow in the middle. That is the light that we see. So think about this as like our eyes are remote sensors. So the sun is shining light onto the Earth's surface, and then we are seeing things because we have sensors in our eyes that pick up red, green, and blue. So you probably heard that we have cones in our eyes that are sensitive to basically the part of the electromagnetic spectrum that reflects as red, green, and blue. So that's why we see colors, why plants are green, why soil is the color that soil is, why we see red in a rose, stuff like that. And that's because we're collecting information, as humans are collecting information through their eyes in that part of the electromagnetic spectrum. Satellites have sensors that can collect information at different points that we can't see to the naked eye. So this looks like ultraviolet, it looks like near infrared, and these different energy wavelengths interact with surfaces with things on the surface of the Earth in different ways. And then that's where we can understand the health of crops. We can understand how things have changed over time by doing math and comparing different things in the GIS. So yeah, there's some great tutorials and videos online. I would honestly just point you to watching a crash course in the electromagnetic spectrum or remote sensing to try and help kind of wrap your head around this. I will talk a little bit more in detail about the different types that are kind of relevant to remote sensing. And with this next slide, we have panchromatic, multispectral, and hyperspectral. If you'll go to the next slide. And so here we'll delve deeper into the distinctions between these three types that are basically collecting information that we can generally see, combinations of what we can generally see. So panchromatic captures a single wide band of electromagnetic spectrum, which essentially produces a black and white image with high spatial detail. What I work with the most, and what folks that are kind of starting to work with remote sensing data, they'll work oftentimes with panchromatic imagery, but most of the time, the most relevant is multispectral imagery or hyperspectral. Multispectral captures data in several distinct spectral bands like red, green, and blue, and near infrared. Near infrared is a very specific and important one for determining crop health and doing some of the indices that, like the normalized difference vegetation indice that I mentioned at the beginning of the call. And basically what you can do is you can apply those different bands, like the red, green, and blue bands and near infrared, to create false color composites that highlight different features like vegetation health. Hyperspectral imagery takes this a step further by collecting data from hundreds of very narrow contiguous spectral bands and provides a detailed spectral signature for each pixel. So this allows you to take it to the next level and get highly precise identification of materials and conditions on the Earth's surface. The other two on the next slide, SAR, synthetic aperture radar, and LiDAR, are two other types. So these types of data, everything that I've talked about so far, is basically a satellite that's circling the Earth, is collecting information as electromagnetic, basically reflectance. So the sun is shining, that energy is traveling through the atmosphere and then bouncing off the surface of the Earth. And then the satellite or the drone is picking up basically the reflected radiation, and that is being generated by the sun. these two are a bit different, synthetic aperture radar and LiDAR, because these synthetic aperture radar is radar and LiDAR is light detection and ranging. So it's like beaming a laser. The sun doesn't naturally produce radar or lasers. So in these cases, the satellite or the drone is actually sending a signal from the drone itself down to the earth and then bouncing it back and collecting the way that it returns. So there's a little bit of nuance there, but these are both kind of advanced remote sensing technologies. Synthetic aperture radar is an interesting one because it uses microwave energy, and it can basically penetrate clouds and darkness. So when the sun's not shining or can't shine through the clouds, or the satellite is on the other side of the cloud and can't see through the clouds, or the information can't bounce back through the clouds, we're kind of out of luck. But synthetic aperture radar can penetrate those clouds and pick up information in dark, so at night, and in all weather conditions. And so this is very helpful for detecting changes in surface roughness and creating detailed topographical maps and understanding things during disasters, storms, or in places where there's a lot of rainfall, stuff like that. And then LiDAR, light detection and ranging, sends laser pulses, as I mentioned, to measure distances to the Earth's surface, and sends out millions of pulses per second, creating highly detailed, like 3D point clouds of the landscape, which then is helpful for things like elevation models. As we move into the future and we start to see more cars that have like automated technology where they can drive themselves, or like driver assist, those are using LiDAR oftentimes to sending out millions of beams of light around the car that we can't see, but the car can see, and it pieces together the environment and can drive itself in that way. The next slide, the primary components of remotely sensed data. I've spoken a little bit to each of these things. Spatial resolution. So that's what's the smallest thing that I can see. It refers to the size of the smallest feature that can be detected in an image. What is the size of the pixel is an easy way. A pixel in the raster image or the satellite image. Spectral resolution, how many different ways can I see this thing, relating to the number and width of the different wavelength bands a sensor can capture. So we just talked about that a little bit. And then temporal resolution, how often can I see this thing? So for example, a satellite might pass the same point on the Earth's surface once every week. A drone, could collect it every day for a week straight, but then it's not consistently collecting, whereas a satellite would be consistently collecting. So that's, a couple of the different components, kind of the size of the pixels, what information is being collected in those pixels, and how often can I see this thing using the specific vehicle or sensor type, right? For example, as well, like the satellites that are collecting information in the synthetic aperture radar part of the spectrum can see stuff consistently through the clouds. But if it's a cloudy day, you're going to miss out on that detection if you're looking for hyperspectral red, green, and blue and near infrared information of the Earth's surface. The next slide, just talking through spectral resolution a little bit more and showing some examples. How it shows how hyperspectral imaging measures the continuous spectrum of light in each pixel, allowing us to identify the unique spectral profiles of different components like vegetation, soil, minerals, or man-made materials. This is, as I've already mentioned, the high level of detail here enables highly precise analysis and differentiation of the surface features. This one is a little bit harder to kind of grasp. It took me longer to understand this. And again, I needed to kind of apply this a couple of times. But keep this in the back of your mind and just, again, think of it as what are the different sensors collecting and what can the different parts of the electromagnetic spectrum show me or tell me about the surface. Spatial resolution, this is a good example on the screen, which basically dictates the level of detail we can discern in an image. As we discussed earlier, what's the smallest thing I can see? So at the left, like higher resolutions, higher spatial resolution means smaller pixels and allows us to identify finer features on the ground, such as individual buildings, vehicles, or even specific crop rows, right? So you can kind of see There's looks like some buildings, maybe a driveway, some paths in the dirt, some different fields of crops potentially. But then as you move to the right, you start to get a lower resolution image, and you can see the pixels starting to show up, or then it's a lot harder to discern what in the image are you actually seeing. And this is a very good visual representation of that. And then the last thing that I'll touch on here before we get into some applications in agriculture is temporal resolution. So as this slide indicates, it refers to how often a sensor can revisit and capture data for the same geographic area. The question here is, how often can I see this thing, as we already mentioned? So high temporal resolution, such as daily or weekly revisit, is crucial for monitoring dynamic processes like crop growth cycles, disaster response, or changes in water levels. So this oftentimes, what will happen is your use case will dictate what temporal resolution you need, what spatial resolution you need, what spectral resolution you need. If you want to understand crop health, you'll want a satellite sensor or a drone sensor that can pick up information perhaps in the red, green, and blue and near infrared, so you can run a normalized difference vegetation index to understand the health of the crops. In terms of spatial resolution, you might want something that's pretty high, so you can kind of localize what you're seeing in the field of your crops. And then temporal resolution, maybe you want to do this analysis once a month throughout the growing season, or once a week throughout the growing season, so you can see where there might be crops that are trending in the wrong direction, and move to them quickly, provide them a fertilizer or a solution to the challenge. Maybe it's a pest infestation, something like that, and kind of get things back on track quickly. So those are the kind of basics of remote sensing. Again, there's so much detail. Like each of these slides alone, we could spend a whole day talking about and getting into the nitty-gritty with. So again, very high level, just to kind of set the stage of GIS and remote sensing. And now what we'll do is get into a couple of applications in agriculture. And I know I've kind of touched on that throughout the presentation, but now we'll give some concrete examples and kind of talk through some of these things. So we'll go to the next slide. One more slide. If we can go two slides to the right, I think, forward in the presentation. Bear with us, I think we're having some issues with the slides again. Let me know if we can move forward two slides to the slide that is titled Applications in Agriculture. One more slide, please. There we go. Okay, and you can actually go to the next slide. One more slide. All right. So now, as I mentioned, we're going to bring it all together and talk about the direct applications in agriculture. This is not going to be all inclusive, and there's probably a lot that you all know and can start to think with your background experience in agriculture of ways that these different tools and data might be able to support things that you all have worked on or studied. I am by no means an agricultural professional, so in that sense, I'm sure I have a lot to learn from you all. But agriculture, I guess, to start off, is inherently spatial. It's dependent on factors like soil composition, which varies across geographies due to the types of minerals that are found there, the different geographical processes, climate, that sort of thing. It's dependent on weather and climate patterns, and it's dependent on land use and precise timing for operations, right? Agriculture is dependent on a lot of different things that happen, a lot of different geological, climatic factors, including human, anthropogenic and human impact on the land and the climate. So with rising global demand for food, increasing climate pressures and finite resources, precision tools like GIS and remote sensing are not just beneficial, but absolutely essential for sustainable and efficient farming to produce the food that we need and to protect and preserve the environments that we need, so that we can continue producing food sustainably for generations to come. The next slide I'm going to touch on again and remind us of these 4 key applications. I'll wait for the slides to catch up. The next slide, please. Perfect. So I touched on these at the beginning of the presentation, but just to refresh, 4 kind of key applications in agriculture that we'll talk about. Again, there are more, but just for the interest of time today, we're going to touch on these. Crop monitoring involves detecting early signs of stress using techniques like normalized difference vegetation index, which is essentially doing math on different bands, the red, green, and blue bands, as well as the near infrared band. And you can do this to kind of allow for timely interventions. You have a little bit of an image in the top left of the screen where you can kind of see, this is a false color image, but this is what the sensors are seeing. Our eyes do not see a field like this, but the satellite or drone can, and it can highlight where crops might not be producing as well as other parts of the field. And in the red examples, the red areas, for example, these are areas where there might not be enough water, or there's a pest infestation, or the crop is unhealthy for this or that reason. But you can't quite see that to the naked eye, right? Because it's still photosynthesizing, it's still producing green. That's all we can pick up on. And if you have large fields as well, maybe you can't get eyes on specific plants. You don't have time to get out there. So you can use the data to monitor crops over large areas. Climate modeling and forecasting, this helps farmers plan planting schedules and irrigation strategies based on predicted weather patterns. We can understand going decades and decades into the past about what the climate has been. And nowadays with modern computers and different things, we can actually predict and model what things are going to look like in the future, especially as things start to change for this or that reason, and the climate warms or cools. We can understand what that impact might be by producing a model. Crop health and productivity, very linked to the first crop monitoring, but utilizing drones and satellite images to guide precise applications of inputs like fertilizers and pesticides, optimizing yields. This is very relevant for drones specifically, as they can not only detect and remotely sense things and understand things about the crops, but then they can help deliver interventions, doing spraying, different things like that. And then land suitability analysis. This application helps match specific crops to optimal growing conditions based on various geographic factors, ensuring specific success rates. So like slope, and even like soil type and different things like that, sun exposure, all that good stuff. We can use remote sensing and GIS to help us understand. The next slide is a use case. I'm going to talk about a couple of use cases here. I think I give 2 examples. And the first one is smallholder farming in sub-Saharan Africa. So this is kind of a broad generalization. Not everywhere in sub-Saharan Africa are facing the same challenges. But let's take, for example, a challenge where farmers are facing erratic rainfall and limited access to advice. So they might be in a very rural context. The rains are inconsistent. They don't have a whole lot of access to to rain, or it's coming erratically. A solution that remote sensing can kind of fill is that remote sensing, we can leverage remote sensing to generate rainfall and surface water maps. And we can even, as you can see in this right one, using specific types of sensors and data, look at groundwater and understand where there might be access to put a borehole or something like that to get access to water that is stored in the ground. On this slide as well, as part of the solution, given the limited access to advice, and in the day and age of technology, as things are developing rapidly, having mobile applications that make crucial data accessible directly to farmers that are able to be connected to the internet, right? These analyses can be run and this information can be shared broadly. And there can be forums where people are discussing, and there's maps and different things where you can better understand the larger context and some of these different data points that are captured by satellites and operated or analyzed in a GIS. The impact, as you can kind of see on the slide, is that then targeted planting, it enables targeted planting, leading to reduced crop failure and ultimately improved food security for these communities. So kind of a high-level, general, broad example of how the technology can be used. And then I have another one, and this is an example in California. So smart irrigation in California vineyards. Here the challenge is severe water scarcity coupled with heat stress, which can significantly impact grape quality. Grapes are a very specific type of crop, and oftentimes in California produced for wine. And so the grapes are very sensitive to these different climate variables, soils, different things like that. And so the solution, you can use drones in conjunction with detailed soil and slope maps, which can also be supplemented or created using satellite or drone imagery to precisely optimize these irrigation zones within the vineyard. So the map on the right of the screen, you can kind of see the slope diagram around a couple of rivers, and then you can also, understand where the sun is going to be shining, how the slope impacts the available light during the day, different things like that, and just giving you the big picture of your plot and where it makes sense to plant, where it doesn't make sense to plant, dependent on those different factors. And then just that other image is kind of an example of what a drone might see going across a vineyard from the aerial perspective. And as I mentioned, the kind of impact here is that it leads to a tangible, better grape quality or crop quality, if we're talking more broadly, substantially reduced water use. So it helps as in those areas where water is more of a scarce resource, using it as effectively as possible. The data and these tools can help us understand that, and then enhance adaptation to the challenges posed by a changing climate, knowing that things ahead are likely going to change, already have changed, and will continue to change. This last slide that I'll touch on, and then with any time, and I'll turn it back to Joseph to see if we have any questions or have time for discussion or anything like that. But I'll talk about looking ahead and kind of opportunities in this space, at least from my perspective and what I've seen. And then, as these technologies are starting to be more adopted and integrated into the work that you all do, of course, there's going to be innovations and ideas that come from your perspectives that are going to be very valuable. But a couple of things to touch on. So anticipating, as we're all starting to get exposed to and work with artificial intelligence and machine learning more. So we're expecting deeper integration with AI and machine learning, leading to more sophisticated predictive modeling and automated decision making. So these look like, for example, going back a couple of slides, that phone, the mobile application, and having like artificially intelligent chatbots that are trained up using this data to be able to help farmers understand these different things, right? Because it's one thing to see a map that has all these different colors and is telling you different things, but it's another thing to understand that map. And it's one thing that the scientific community can sometimes is a shortcoming, where there's the information isn't communicated in a way or for example, even in a local language or a local dialect where that information needs to be received. So I think there's going to be a lot of opportunity with artificial intelligence and machine learning in that sense, and also just in what we're able to do computationally. Things are speeding up really fast. The amount of data that we're collecting, the amount of data that we can analyze at one time and understand is increasing, and then the modeling is going to, just increase exponentially in its accuracy and its ability to just consider different externalities and things as these computers get smarter and stronger at running these different analyses. Another one, real-time alerts for floods, droughts, and pest outbreaks will become more common, enabling proactive responses and minimizing losses. This is a huge one. I work pretty closely with some humanitarian partners in kind of the disaster response setting, and these real-time alerts save lives. But when the information isn't highly accurate, it can be a little bit of the boy that cried wolf situation where essentially what I'll say is that we're just getting better at understanding severity and being able to forecast and understand where risk exists, and then be able to disseminate and communicate information when there's impending risk. And then of course as well, like getting away from that risk, supporting the logistics, as we mentioned at the beginning, right? Understanding the roads that people might be able to travel on, and route optimization, different things like that are all spatial problems, things that you can use GIS for. And then the last one I'll touch on is the growth of open data platforms, such as Digital Earth Africa. There's a screenshot of one of their dashboards up there, but it's really, it'll work to democratize access to the vast amounts of geospatial information. And then this will kind of foster this innovation and sustainable agriculture practice and community of practice globally, right? We're kind of at the tip of the iceberg and at the very beginnings of a lot of these large scale continent wide geoportals, essentially, that provide that access to the different data, and people are starting to have it more and more at their fingertips to be able to understand and act on this different information. And so there's going to be a lot that happens in the next couple of years around this, and then it's all going to be turned on its head as well, with the changes that we're going to see in the kind of AI and machine learning realm as well. So it's a very exciting time. But again, as kind of mentioned at the beginning of this call, it's a tool and a technology that we can all use to better ourselves and better the work that we're doing, for ourselves and for people that depend on it, especially in an agricultural sense, and being able to feed people and feed the world, and also take care of the environment and make good decisions about where and when and how we're farming. So with that, I will turn it over to questions or back to the host and see where we go from here. But thank you so much. I'll share my contact information or make sure that these slides are available, and we can, available for questions and anything like that.
Okay, thank you so much, Mr. Simons. It's actually a well delivered information. It's an insightful section. Yeah, you really did a very good job giving us the breakdown of how this GIS and remote sensing actually works and how it's applied to agriculture, relation to equipment, sensors, and data. So we have a lot of questions here as well for you from our participants. So trying to, let me just start bringing them up. Okay. So then this person is asking, what are the requirements for smart irrigation during dry season farming? Okay.
Yeah, that's a very good question. And again, like I mentioned, I'm not as much an agricultural professional or have the right answer maybe to this question around smart irrigation during the dry season. I think there's a lot of different things, as I kind of mentioned in the presentation, that can help folks better understand that for themselves in their different contexts, and understand the climate that they exist within, and those kind of normal practices, of course, at the local level and through indigenous knowledge and stuff like that, but then supplemented and then maybe using different models, using kind of weather and climate data from around the world and analyzing the system as a whole, you might be able to better understand the requirements for smart irrigation during the dry season. But yeah, I don't know that I can fully touch on this based on my expertise and just the breadth of my knowledge with GIS and remote sensing.
Okay, thank you. We then have this.
Are there drones? The next question is, are there drones that are fitted with LiDAR technology? And I have never worked with a specific LiDAR drone, but I have to imagine that there are. So the thing about all of these different sensors, synthetic aperture radar might be a little bit of a different case because of the way, without getting into the nitty gritty of that technology, but it requires a pretty large sensor. But oftentimes, a lot of these sensors can fit. They're very small, right? They're like a camera lens, or they can fit within a bread box. LiDAR, I haven't specifically worked extensively with, but I imagine that yes, there are drones that are fitted with LiDAR technology. I know it can be a relatively expensive one, and so it would just depend on the use case. I will say that there are other data sets out there. There's a couple of them that have, if you want to use LiDAR to potentially put together like a digital elevation map or a surface elevation map. There's other like global data sets, and I can share some links to some of those that provide that information. It depends on the scale. Some of those are the scale might be too low, or the resolution might be too low for what you would need. Like for example, a specific plot or agricultural plot. But yeah, the short answer is yes, there should be, I imagine.
Okay, thank you. Someone is asking this question: what specifically relates coding with Python to GIS? You have
So what
anything to say?
specifically
Okay.
relates coding with Python to GIS? It's a good question, and I guess the way that I'm interpreting it is like why Python versus R versus some different languages. And to be completely honest, I'm not sure. I think a lot of the early geospatial platforms and GIS software was built using Python, and so it's just a language that has uh, come to be kind of normalized and adopted across the community. Yeah, but I'm not for certain on that question. Actually, I would maybe look it up online and see what you can find, because there might be more nuance to the specific packages and tool sets that Python has. I know for a fact that there are a lot of geospatial GIS specific tools and packages built in Python, um, but beyond that, I am not sure why Python and GIS are so closely married.
Okay, thank you. This is what advice?
What advice, the next question, thank you for this one. What advice do you have on people like us going into modern farming and integrating it with precision agriculture? I think the advice I would have is advice that it seems like you all are already taking, in taking a course like this, being a part of a cohort, learning these skills. And I've worked closely with Femi, and I'm sure other folks that you're working alongside, is just stay on top of it, try and learn as much as you can. Like I mentioned with the GIS softwares, like play around in them, download QGIS and download a data set and kind of try your hand at things. But even at just the high level, if you can understand the value, and it doesn't necessarily need to be you running these analyses, but as like an agricultural professional, a farming professional, being able to understand and then speak to and kind of like preach the good gospel around this technology and the impact that it can have, I think is a very important important thing moving forward. But I would just say things are changing really fast in today's day and age. AI, there's things that, already in the last year have changed and evolved. And so I think as much as you can kind of stay on top of that, I know it's a lot of information, but keep doing refresher courses, and kind of keep as much as you can your finger on the pulse of the way that the technology is evolving and moving, I think will only benefit. And then I think as much as you can have that technical cap on and understand the technology and the opportunities there, don't lose sight of, I think I've seen it happen multiple times in this, it's an exciting place to be, this very forward thinking technological place. But sometimes too, things can be a little bit over engineered. So stay rooted in the challenges that you're facing or what you're seeing on the ground, and make sure that the solutions that you're trying to use are fit for purpose, because there's a lot of different things that you can do, but not all of them will make sense. And there might not be one that makes sense, or there might be a more traditional or localized solution to a challenge. Just because the technology is there doesn't mean it's always the best option. So don't let it cloud out or take away from the other types of knowledge and tools and technologies that are out there. Absolutely. I will share I will put together a follow-up email, and then maybe the folks at Precision Agriculture can help send out an email with some of these, and I'll share my contact information as well if people would like to reach out, and I'm happy to share any and all resources.
Okay.
Yeah, good question again, around the skills needed to become the best agricultural GIS practitioner. I think again, there's online resources, and I'll link to some of them that I found helpful. But just take advantage of online tutorials, download QGIS, and start working in the software. Or, for example, it might not be a specific agriculture GIS course, but if you find a boot camp or some sort of curriculum or course, similarly to the cohort that you are in right now for agriculture and precision ag, if you find just a basic one on GIS, just to learn some of those fundamental principles, I think that would be super valuable, just to get your foot in the door and be able to start working on that. Other tools, the next question, other tools that can be used to access data aside GIS. So there's a lot of different tools that, accessing data, for example, there's a lot that you can do in Excel, and a lot of calculations that you can run. If I'm interpreting the question right, that there are very, very powerful options with just those kind of more basic tools that a lot of people are trained on and have access to. Access data aside, GIS, I feel in terms of collection and accessing data on dashboards and different things like that, but using mobile collection devices, GPS things like that. Other platforms I'm sure are out there. I'm not sure, I guess beyond that, or if you can clarify a little bit more on the tools that you might be specifically asking about. Yeah, so the minimum requirements or legal requirements for flying a drone for agricultural purposes. Great question, and that one that would definitely be better directed towards maybe Femi or some other folks from the Precision Field Academy. I am not for certain. I know where I'm based here in the United States, you have to get a specific license to be able to fly a drone. And then I think depending on like the size of the drone and the payloads, so like what like sensors and different things. And I imagine that varies from like state to state, county, provincial level, like to maybe even the county level. But I think generally, and Precision Field Academy would be a great resource for kind of better understanding that, or what steps you would need to take to flying a drone for agricultural purposes. I can't quite speak to that in too much detail.
Okay, just give me a few seconds. I'm trying to check for other questions we have here from a participant. Okay, I think I've seen one already. Okay.
All right, so we have the question, what exact data sets or source data can be used to determine the risk of flash flooding in an area? So this is a really good question and a really pertinent one in today's day and age. So digital elevation models are really valuable. So like talking about the LiDAR or other radar, synthetic aperture radar data sets that can detect essentially and help us understand where floodplains are, and then looking at long-term flood data and climate data to be able to model and understand the frequency and kind of the intensity of some of these floods. But I think risks of flash flooding in an area, there's a lot of use cases and there's a lot of organizations that are working on this specific and have like global models and that you can kind of plug and play with in different geographies around like risks of flash flooding that are valuable to check out. And then of course, like tied with that is the like early warning system that are probably place by place dependent in the case of a flash flooding event or a heavy rainfall that's coming in. Of course, like weather forecasting and different things is a type of like geographic information that we all interface with on probably a day-to-day, depending on where you're at in the world and how well the forecast, like the local forecasting office. Of course, there are some like global forecasting data sets and stuff like that for weather, but it depends kind of on where you're at to get the kind of like finer scale weather forecasting. Can we really use precision agriculture for livestock farming, such as poultry farming, goat farming, and so on? I think absolutely there would be use cases. I think it depends on what specific questions or challenges you'd be facing, like in poultry farming or goat farming. I'm not as familiar with either of those specific fields or areas of expertise, so I can't necessarily say the specific things that a poultry farmer would be needing to understand or want to understand, and a goat farmer. But I have to imagine that there would absolutely be a connection in a way that it would make sense to use precision agriculture for livestock. Yes, this next question. Thank you so much, Hassan, for this one, because it's a very critical point. Hassan is saying generating information using sensors is just one part of the puzzle, but the biggest challenge is interpreting the information. Presently, are there softwares that can interpret the data, or is it still purely based on human intelligence? Thank you very much. Yeah, and this is where, like with the last slide that I presented on, the AI and machine learning. So there's still at kind of the current day and age where we exist, is there's still, there needs to be a person at the end of the line that's kind of interpreting the data. I specifically haven't used or haven't been made aware of, for example, a chat bot like ChatGPT or something of the likes, where you could take a geographic data set and drop it in and say, like, kind of prompt it with what you wanted to do. but I have to imagine that we're not far from that time. I think the closest, at least for analysis, that we can get is using some sort of AI or software that can help you come up with a script or a code to analyze or walk you through different steps to analyzing it. But I think the interpretation part is still purely based on human intelligence. And then that's where it's important, going back to a couple questions ago, as agricultural professionals and folks that are participating in this field academy, is that you all exist in a very valuable place. And the value would only increase as you start to understand these technologies more, because you are, I'll give the example of myself, right? Like, I studied global health, and so I understood the context and the challenges and different things in global health. And then I also studied GIS. I studied them separately, but then as I started working professionally, I was able to marry the two and understand the technology thoroughly enough to where I knew I could interpret the data and understand it and apply it to the challenges that are being faced in global health. So as much as you can work at the intersection of two fields using GIS and these tools as the technology that they are, but then be an expert that's rooted in context and in that like local context and knowledge of the specific thing that you're trying to interpret, right? That's where the interpretation comes at the end, when it's like, okay, what is this data telling me, and how should I interpret it based on the world around me or what I'm trying to solve? Yeah, kind of a rambly answer. I don't know if that's helpful, but it was a great question, and something that I think, we'll all be pondering in the next, years as things start to change and AI becomes more and more integrated with our day-to-day. How can geographic information systems be used to analyze and visualize spatial variability in soil properties? Yeah, so this is a great question, and it's kind of a fun one. It goes back to like the electromagnetic spectrum and just using satellites basically at high enough resolution can actually interact with different like minerals and different things in like the soil composition to be able to understand like the variability. You can also assess like biomass content and different things like that in the soil. Obviously, you can't necessarily get the same like data out of like, doing some chemical tests, because inevitably it's going to become like the soil and those minerals and different things are like at too fine of a level. But then on the other end of the spectrum, like GIS can help like more broadly understand that, and then it can help you identify how and when and where to maybe potentially apply fertilizers or different things to boost soil when it's not as strong. But that's a really good question, and something that I would also suggest like poking around online to see and seeing what you can learn about that, because I'm sure there's a lot of detail out there online. The next question I'm seeing is, does GIS help to navigate and respond to emergency? Absolutely. This is a huge sector, I would say, in GIS, right? Because navigation is understanding routes, like where you need to go in space and time. And then emergencies, for example, like if there's a disaster and an earthquake, like infrastructure gets damaged. So you can do before and after assessments to understand like where there were roads, are those roads still accessible? Can we still navigate through that path? You can do kind of rapid assessment, especially using drones. And then like in the health use case, for example, helping us navigate and deliver vaccines where they need to be, food, aid, different things when responding to emergencies are a huge field. This is like, absolutely, yes, GIS, it helps a lot with navigation and responding to emergency. Even at the simplest level, you need a map to kind of know where you're going. If you're going to a place that you never have been before, or you're trying to get get from point A to point B. Can GIS let us know what to grow in a particular area? I think it can help. I don't think that it could tell you one way or another that you should plant. Well, I think it could help you understand, again, like characteristics about the soil, characteristics about the slope, characteristics about the climate, that then all influence what crop would make sense to grow in a particular area. So yes and no. I think you still need to have kind of a good conceptual background and understanding of where you are, understand the like historical context, the climate context, which GIS can help you do. But then, to understand which crops to grow when, I think it can just support you with more data to make that decision, rather than, right, that's all GIS is at the end of the day, is it's just data, working with data, and it's helping you make a decision that you were going to make anyways, at least in this specific example, but you're making that decision in a more informed way. So it can definitely help you do that and know what to grow in a particular area.
Okay. So I'm going to be taking the last question now.
Okay.
So set out and analyze pH for cultivation. Is it possible? There are a lot of questions, but I'm just trying to identify the most suitable area. How do we analyze pH?
Okay. How to analyze soil type, pH, elevation, and rainfall patterns to identify the most suitable areas for sweet potato cultivation. This is a great question, and I don't possibly have enough time to answer it in all the detail. And again, would recommend doing some research online. But satellite imagery, I'll just answer more broadly. It can absolutely help, and different types of remote sensing information can definitely help you analyze pH, elevation, and rainfall patterns. And so I imagine, based on doing a specific analysis in a specific place, on those different things and comparing it against sweet potatoes and cultivation, you could definitely you could find success doing that.
Okay, thank you so much, Mr. Simos. It has been an insightful section with you from the beginning of this program, and now we are wrapping up, so we'll be closing in a few minutes. All right, thank you so much for coming. Thank you for honoring our invitation. We sincerely appreciate this. So I just quickly want to say this. Do you have maybe like a word of encouragement or a closing remark you want to give to our participants learning this program? So before we close the program, we can do well to share here.
Yeah, I think I've kind of said my piece. I guess just thank you for the opportunity. I'm happy to be here and happy to share. And there's a lot that I'm still learning, and a lot that I will continue to learn. And I just encourage you all to seek out opportunities where you can meet different people and learn from their experience, and kind of grow, especially in these kind of technologically advanced GIS, AI, machine learning, these different fields, and kind of discover and be curious about the tools and technologies that are out there to help us all do our jobs better and make more informed decisions, and kind of impact the world and help others, whether that's increasing crop productivity or responding to disease pest outbreaks in crops, across the board. I think there's a lot of different ways that you can take these tools. It's just a tool, and I'm in the camp of, I like to think, about having as many tools as I can in my toolkit to help me solve challenges, and this is just another one. So that would be my word of advice: is just pursue opportunities, kind of try to stay on the cutting edge, or not even on the cutting edge, just understand some of these concepts, and being able to speak to them will be valuable.
Thank you so much, Mr. Simos. It's a pleasure to have you here. And on behalf of the Precision Agriculture Incubation Program and the entire Britionfield Academy team, I'm saying a very big thank you to you. Thanks so much for honoring our invitation. So see you next time.
Okay.
It's a pleasure. Yes. You
Yeah.
have a good day. All right. Bye for now.
Thank you so much. Bye, everyone.
All right.